Hello, good morning, everyone. This is Dr. Sharif El-Gamal, and today we are going to continue our videos about reinforced concrete design according to the British standard. Today we are going to continue with two-way slabs. This is part two. In part one, we talked about introduction and general steps that you need to use to design two-way slabs, tables you need to use also to design. And in this part number two, we are going to solve an example of the first type of two-way slabs, which is the simply supported two-way slabs. Okay, and in this example number one, it is required to design the reinforcement for rectangular simply supported slabs having effective dimensions of 4.5 times 6.3. So it is a simply supported slabs with a short span 4.5 meters and a long span of 6.3 meters. The live load here, we used a high live load, which is 10 kilonewton per meter square, and the concrete compressive strength 30 megapascal, F yield 460, and we used a beam width of 230 millimeter. So how to start solving this one and to find the reinforcement, making all required checks? Let's see together. The first thing to do is you need to classify, is this a one-way slab or this is a two-way slab? So we can do that by checking the ratio between the long span divided by the short span. So Ly over Lx, long divided by short, equals 6.3 divided by 4.5. So this is 1.4, which is less than 2. So if it is less than or equals to, this is two-way slab. So 1.4 is for sure two-way slabs. So in this case, we need to design it as a two-way. So we have to find first, starting by initial proportioning, you need to find the thickness, the depth, and the total thickness of this slab, so you can use it later on to get the self-weight of the slab. So as you know, from table 3.9, the basic span to depth ratio, you can see here, this is table 3.9 in the British standard. So this is simply supported. The basic span to depth ratio is 20. So we can use this one, it is 20, and we assume modification factor of 1.3. Using these two values, the minimum effective depth equals the short span divided by the basic span to depth ratio, which is 20, multiplied by the modification factor, which is 1.3. Let's substitute these values. So 4.5 meters, you have to put it in millimeter to get the thickness in millimeter. So 4,500 divided by basic span to depth ratio 20 times multiplication factor of 1.3. This will give us 173 millimeter. So you can round it to a bigger value or lower value because you have to check later on. So here in this case, because the live load was somewhat high live load, so I round it towards 180 millimeter. Then the second step is to check the cover that we need to use. It will depend on the durability and fire resistance. For durability, we have a mild exposure and concrete strength of C30, 30 megapascal. So if we go to table 3.3 in the British standard, so mild exposure with 30 megapascal, so mild with 30 megapascal, it is 25 millimeter. So this will be the concrete cover in a case for exposure, table 3.3. Also, we have to check for fire resistance. For fire resistance, this problem, we assume that we have a fire resistance of 2-hour fire resistance. Okay, it's not given here, but I assumed it in my calculations. So from table 3.4, let's go and see here. For 2 hours fire resistance, you will go here, and we are talking about floors. Okay, and it's simply supported, not continuous. So the value here or the concrete cover is 35 millimeter. So we'll use it at 35. So you have two values, 25 from table 3.3 and 35 from table 3.4. So we take the larger values from these, it is 35 millimeter. So we calculated now the depth is 180 millimeter, the cover is 35 millimeter. We need to find the total H or the total height of the slab. To do that, we assume 10 millimeter diameter bars. So the overall depth, what we call it H in this case, equals D. plus cover plus phi over 2. The D is 180. Cover, we found it is 35 from the fire resistance. It governs the concrete cover, plus diameter over 2, 5. So this gives us a total thickness of 220 millimeter. By doing that, you finish the initial proportioning. So we need to go to the second step about final proportioning, starting by calculating loads, then bending moments, and making our design. So to do that for the loads, we have the self-weight always equal the thickness of the slab in meter times the density of the concrete, as assumed here, 24 kilonewton per meter cube. So 220 divided by 1,000 to put it in meter. So it is 0.22 meter times 24. This will give us a self-weight of 5.28 kilonewton per meter square. Then live load, it is given in the problem here. And as I told you, it was high here. So it is 10 kilonewton per meter square. Usually it is between 2-3 kilonewton per meter square, but in this example, I used a higher value. Like if you have a library or you have a store, so you will have a high live load like in this case. Okay, so once you calculated the self-weight, live load, in this case, we didn't use any finishing. Okay, because if you have finishing or if you have services or any other dead loads, it will be added here between the two values. So here we have the self-weight, we have the live load. Now we can calculate the ultimate load, which we call it N or sometimes W ultimate. It equals 1.4 times dead load plus 1.6 times live load. It gives us a big value here, 23.4 kilonewton per meter square. We are going to use this value to get the bending moment in both short direction and in the long direction. So let's move to calculating the reinforcement. And to do this, we need to find the bending moments in the short direction and in the long direction. So to do that, from table 313, we have to find some factors, alpha Sx and alpha Sy. To do that, we need the Ly over Lx. It is equals 1.4, as we saw in the previous slide. And this two-way simply supported, and the Lx is 4.5 meters. So because it is simply supported here, we have to use table 313. So table 313, and keep in mind that Ly over Lx is 1.4. Let's go and see here. Ly over Lx, and the value is 1.4. So we can get alpha Sx and alpha Sy. Alpha Sx equals 0.099. Alpha Sy, it is 0.051. We are going to substitute these two values into equation number 10 to get the moment in the short direction, and we substitute alpha Sy here into equation 11 to get the moment in the long direction. So getting the moment in the long direction and in the short direction, we can use equation 10 and equation 11, and this is alpha Sx, we get it from here, alpha Sy, we get it from this value here, and NLX square, it is similar in both equations. So we are going to substitute these two values into these two equations. Let's see together, and we'll see how to get the moment. So from this table 313, we found that alpha X is 0.099, alpha Sy is 0.051. Substitute into equation 10 to get the short span steel. So we have to get the moment in the short direction equals alpha X n Lx square. Alpha X is 0.099. And N here is 23.4. We just substitute it here. And Lx always use a short span. So 4.5 square, okay, multiplication of these values here, it will give us 46.9 kilonewton meter per meter width. Okay, once we get the moment, so it will be very easy to calculate the reinforcement. As usual, we have to get the K equals M ultimate divided by FCU BD square. So the M ultimate is 46.9, and don't forget to multiply by 10 to the power 6 to make it as Newton millimeter instead of kilonewton meter, divided by FCU times 1000 millimeter, which is the width strip that we always take and we solve for slabs. And D square is 180 square. So this will give us a small value, 0.048, which will be for sure less than 0.156. It means this will be a single reinforced section. We don't need compression steel to add here. Once you did that, you have to calculate the Z over D. Z over D value from the code equals 0.5 plus square root of 0.25 minus K, that you calculated here divided by 0.9. So the only value we put here is the K and gives us a value of 0.94. Okay, just keep in mind, if this value here is greater than 0.95, so we have to use it as 0.95. Once we calculated the Z over D, so we can go directly to calculate the area steel required or required steel reinforcement equals M ultimate divided by 0.95 F yield times Z. Okay, substitute with the values here, and the Z here, it is 0.94 times D. So this will be the required steel reinforcement. This required steel reinforcement, we can use a table to calculate this one. So we used here T12 spaced at 150 millimeter spacing, and the AS provided equal 754. And to show you how we get this value, I will show you the tables that we are using here, which is table number 2. From here, if we want to use 12 millimeters or 10 or 8, so you can choose the diameters that you want to use, and the spacing that you want to use, it will give you the area of the steel provided. So here, if we use 12 millimeter diameters, and just to go here, the areas that we have, I will go back and post the check. Okay, last viewed. So the area required, it was 634 millimeter square with 12 millimeter. Okay, this is 5, this is 646. So theoretically, we can use T12 spaced at 175 millimeter, and the AS provided will be greater than the AS required. In this problem, even I did not use a spacing of 175. I moved to a more amount of steel reinforcement, which is T12 spaced at 150, and I use 754. Why I did that? Because when I use this area, and T12 is based at 175, and I checked the deflection was not safe. It was like very close to the safe value. So what I did, I increased the reinforcement ratio or the reinforcement from 646 to 754, and I checked the deflection, it was safe. So this is why I chose T12 spaced at 150. So this will be the ASO provided, 754, and let's go back here. So this is 754, and the reinforcement T12 is based at 150. This is, of course, in the short directions per each meter in the short direction. Then we have to repeat this, but in the long direction. In the long direction, we'll use equation 11, alpha sy in Lx square, and this is the alpha sy that we got it from the table, and will give, of course, bending moment, which is for sure will be less than the bending moment in the short direction. So keep in your mind that always the moment in the long direction will be less than the moment in the short direction, because always the alpha sy will be less than the alpha sx. Okay, so by substituting these values here, again, we can calculate the K. The K in this case is even lower than the previous one because the moment is even lower. So calculate Z over D. You can find that the Z over D in this case was 0.97, which is greater than 0.95. So the code is telling us we cannot take it greater than 0.95. So we'll keep the Z equals 0.95 times D. Okay, substituting into this equation to get the area of the steel, required steel reinforcement, M over 0.9 F yield times Z. So this is the moment in the long direction. 0.95 F yield times Z. Z in this case, we use the maximum value allowed by the code, which is 0.95 times D. And this will be the AS required. This is 324. Let's go and see in the table. 324 will use 10 millimeter in this case. So 314 cannot work. It's 324, so we have to use bigger value. So it will be 349, and in this case it will be T10 is based at 225 millimeter, and the AS provided will be 349 millimeter, and this is what we used here. T10 is based at 225, and AS provided equal 349. By doing that, we design the slab in both short direction, and we got the reinforcement, and we got the reinforcement also in the long direction, as we have seen. But this is not the end. You have to make your checks. So we can start by checking deflection. And this deflection is always, we start by M over BD square. It is this value. And the M here, it will be always the maximum positive moment in the span. The maximum positive moment, which will be always will be in the short direction. Then from table 310, we have to get the stress in the steel reinforcement from this equation here. Substitute AS required divided by AS provided, which we get it from the previous slide. And if we yield, keep always beta as 1 because no distribution. And this is the F steel equals 259 Newton per millimeter square. Substitute this value in the equation into the equation of M. M equals 0.55 times or plus 477 minus Fs, which is this value here. It is 259 divided by 120 times 0.9 plus M over BT square, which we got it as the first step here. Substitute all the values and we get a modification factor of 1.32. So your deflection check is almost finished. You have to check now from limiting span to depth ratio and comparing with actual span to depth ratio. Limiting span to effective depth ratio equals the effective or the basic span to depth ratio, which we get from table 3.9 and we used at the beginning. It was 20 multiplied by the M that you calculated. So 20 times this M, which is 1.32, it gives us a value of 26.4. This is the limiting value. How about the actual span to depth ratio? Actual span to depth ratio, always get it from the short span. So it is 4,500, which was the short span, divided by the actual depth that we used. It is 25. And if it is less than the limiting span to depth ratio, as in our case, it's very close, but still less. So the deflection is okay in this case. Once we calculate the deflection, you have to check for the shear. And checking for the shear, we have to get the shear value from table 315 for Ly over Lx point equals 1.4. Go to table 3.15. You have different values here. This table is longer, but I just cut it here to show you at the end. You have your 4 edges discontinuous. 4 edges discontinuous. So the value here is 0.43. So let's go back and we use this value here. So the beta Vx equals 0.43. Substitute into equation 19. Beta Vx times N times Lx. Okay, the N is 23.4. The Lx is always the short span, and this is the beta Vx. We have a shear force of 45.3 kilonewton per meter width of the slab. We have to check for this shear. So we get the shear stress equals the shear force divided by B times D. It equals 0.25 Newton per millimeter square. We have to compare this one with the VC, the shear stress carried by the concrete, to be sure that this shear stress is less than the shear carried by the concrete. Also, we have to check that if this value is less than the maximum shear stress, the ultimate allowed by the code. And for sure, as I told you, in slabs, always the shear is small in the two-way slabs. And of course, you can see it is much lower than the V ultimate. So it means it's okay. We can now go and compare it with the VC. To get the VC, we get it from table 3.8 using this equation here. VC equals 0.79 times 100 over AS over BD to power 1 over 3 times 400 over D to power 1 over 4 divided by gamma M. Gamma M is always 1.25. 100 area steel divided by BD, we can calculate from here. And here I used area steel equals the AS provided divided by 2, assuming that I will cut 50% of the steel and I will extend 50% of the steel. So I used here AS provided divided by 2. And this simply supported slab. And you should be sure like that this value 100 AS over BD will not be greater than 3. If it is greater than 3, we use 3. But of course, in the slab, it is always less. 400 over D should be greater than 1, which is our case. Substituting all these values here, we got a shear VC equals 0.51 Newton per millimeter square, but this is not the end because this value is calculated for a concrete compressive strength of 25 megapascal or less. So in our case here, we have a concrete compressive strength of 30 megapascal. So the values that we calculated here should be multiplied by FCU divided by 25 to power 1 over 3, which is 30 over 25 to power 1 over 3. So it increased a little bit from 0.51 to 0.54 Newton per millimeter square. And for sure here you can see that the V, the shear stress, is much lower than the shear carried by the concrete. So it means the shear is safe. Okay, so we checked deflection, we checked shear, and now we need to check for cracking. For cracking, you need to check for minimum steel reinforcement ratio. So the minimum steel from table 325 here for solid slabs with minimum reinforcement for steel of 460 megapascal, the minimum reinforcement ratio is 0.13%. So from here, we can calculate the minimum steel reinforcement, 0.13 BH, 0.13 BH divided by 100. So 0.13, and always B is 1,000 millimeter in slabs, in solid slabs. H is the total height, 220 divided by 100, was 0.13%. So it gives us a reinforcement of 286. And if you still remember, for the short direction and the long direction, the reinforcement was 754 and 349, which is greater than the minimum. So it means this is okay for the minimum reinforcement. Also, we have to check for the spacing. The spacing from this close here, it tells us that the maximum spacing allowed by the code is the minimum of the one of lesser of these two values, 3D or 750. The 3D will govern, it will give us a value of 540 millimeter. So our spacing, you can see for short direction, it was 150. For long direction, it's 225, which is both of them are less than the maximum spacing. It means the spacing are okay. So by doing that, we checked the cracking. Now we can check for some detailing. Here I'm going only to talk about the end anchorage. End anchorage, if the V is less than VC over 2, which is our case, so the end anchorage is the greater of 30 millimeter, or end bearing divided by 3. End bearing, it means the width of the beam. So in this case, we have the width of the beam 230 divided by 3. It will govern because it will give us 77 millimeter, which is greater than 30. So this will be extended beyond the center line of the support. And the last thing to do here to make a drawing, a plan showing your reinforcement. Okay, keep in mind that in short direction we have T12 spaced at 150, and in the long direction we have T10 spaced at 225. So we start by the short direction. In the short direction, T12 is based at 150 in the short direction, and it will be for the whole slab. Okay, in the long direction also, this is the long steel. We are going to use T10. It's based at 225 millimeter, and this will be the end of this video. The coming video will, in the coming video, we'll talk about another design example of two-way slabs, but restrained two-way slabs. And if you want to check my previous video, it was the introduction on all information you need to make your design. Thank you, and see you in another video, and goodbye.